Well, hi guys. We're going to have a look today at kinematics, and specifically we're going to look at the formulae which you can use for constant acceleration scenarios. I'm going to derive these formulae and then we're going to use them, okay? You might have seen them before if you study high school physics, okay? Particularly in year 11. Oh right, there are four formulae which can be derived for kinematics, that is motion in one direction we're studying, when the acceleration is constant. I call these the license to drive formulae, and your license to drive them is when the acceleration is constant or the acceleration is uniform. That's another way of saying constant, but you do not have a license to drive them at all if the acceleration is not constant. So please don't break the law and drive without a license, okay? So starting with dv dt, derivative of velocity with respect to time is acceleration. That's a constant. That a is a constant, all right? Now what I'm going to do now is I'm going to anti-differentiate that to get an equation for velocity, okay? Yep, that's a constant, and when we anti-differentiate with respect to time, what do we get? We get that, okay? We get v, that's on the left-hand side, after anti-differentiating this term here. Then on the right-hand side, we get a times t plus the constant of integration, okay? Because we're anti-diffing with respect to t. That's at plus c. Okay, now we're going to substitute. If the initial velocity was u, okay, we'll substitute that in for the velocity at time t equals 0, and let's see what we get. Okay, time t is 0, v equals u, therefore we get, right, we get v is u, okay, that's the initial velocity, and we've got is a times 0, because t is 0 plus c, alright, and then that leads to c is equal to u. So now we can rewrite this equation up here with u instead of the c term here, and then what do we get? There it is. That's equation 1 of the Academy Award winning license to drive formulae for constant acceleration. Final velocity equals initial velocity plus acceleration times time. This is the constant acceleration we're talking about here. Alright, now having done that, guys, we're going to anti-differentiate again, okay, with respect to t. We know that v is dx dt, the derivative of displacement with respect to time. So let's write that out. We'll say that v is actually dx dt, and that equals u plus at as found up here. Now we're going to anti-diff that again, guys, and we're going to get, therefore, x equals, anti-diffing this, ut plus a half at squared, plus another constant, which I'll call d. I don't want to call it c because it could be a different constant, right? Now let's put some initial conditions in again. If we say that the displacement or the position was 0 at time equals 0, and we substitute that into the above equation here, what you'll get is x is 0, t is 0, t is 0 here, and so you've just got 0 terms all along there except the d term, which means that d must be 0. And therefore, we get this. X is ut plus a half at squared, and the d term is 0. Okay, so we just get that. And that is equation 2 of our license to drive celebrity formulae, okay, for constant acceleration. Alright, now, a change of pace now. What we're going to do is we're going to take this formula here, and we're going to express t in terms of v, u, and a. So it would be v minus u over a. That would equal t. And then we're going to substitute that formula for t into here to eliminate t from this equation. Okay? So that's what we're going to do. From equation 1, t is v minus u over a. Then we're going to put that into equation 2, and what do we get? A big mess. That's what we get. So we get x is u times t, where t is this, right, plus a half times a times this thing squared. Now, we better simplify that before too much more time goes by, because it's looking like a big mess. So what would we do, guys? Well, there's the first step at simplification. what I've done there, as you can see, there's not much happened to that term, but this term here, I've basically said that this is v minus u all squared over a squared, and a goes into a squared a times here, and there's a 2 from the half. Okay? Now, in order to get rid of that nasty denominator, why don't we multiply both sides of this thing by 2a? Alright? And what's going to happen? We get 2ax equals, okay, 2u, because the a part of it cancels out, into v minus u plus v minus u all squared. Alright? Now, let's just multiply this thing out and see where we end up. Let's see if that looks right. 2uv minus 2u squared plus v squared minus 2uv plus u squared. I think that is right. Now, there's going to be some cancellation throughout the nation here. Where is it again? Aha! This and this. Right? That's going to go, so let's just do that. Goodbye, Mr. 2uv. And of course we've got a u squared here and a minus 2u squared there, haven't we? So that ends up being v squared minus u squared, the familiar 3rd Academy Award winning formula for constant acceleration. There it is. V squared minus u squared equals 2ax, or v squared equals u squared plus 2ax. That's number 3. Fills us with glee and yippee. Now, there is a fourth one. It's a little bit different, and you don't very often use it, but I'm going to derive it anyway because it's pretty important in the overall scheme of things. Now, starting with this new starting point here, guys, average velocity, as you know, is the change in displacement over the change in time, isn't it? Yes, it is. Now, if the change in displacement equals delta x, which in relation to a 0 origin starting point would just equal x minus 0, in other words. Alright, so we'll just call it x if 0 is the starting point. And secondly, if the change in time, this denominator term here, we've just dealt with the numerator term there with the change in displacement, now dealing with the denominator. If the change in time is delta t, and that just equals t minus 0 if 0 is the starting time, which of course it is, then what do we get over the screen? That's what we get. And we get this. The average velocity must be just x over t, right? That's your delta x, x minus 0. That's your delta t, t minus 0. So the average velocity is just x over t. Alright? Alright, now that's Mr. Star equation, alright? Now, the plot's thickening a bit here. If u is the starting velocity, and if v is the final velocity according to the conventions we've been using up to this point in this session, let's do a little graph of that. Now, look very closely, my dear friends. This is the point 0 and u, 0 time and u initial velocity. This is the point here, t, final time and final velocity, okay? And we're dealing with a constant acceleration scenario, which means that you have a constant gradient of the velocity time graph, because after all, if the acceleration is constant, then the velocity goes up at a constant rate, right? Acceleration is a rate of change of velocity, or the gradient of the velocity time curve, okay? Constant acceleration, a constant gradient. Now, look at this. We've got a straight line here, a straight line, and at the ends, the 2 points at the end of this straight line, this green line here, we've got u is the velocity here, v is the velocity there. Now, what is the average? What is the average of those two values, u and v? Okay, it's a straight line segment. The average value of velocity is the midpoint, or just u plus v over 2. Okay, that's what I want you to get. Okay, so let's go through it. Because the velocity time graph is a straight line trajectory for constant acceleration, that is, the gradient of a velocity time graph is acceleration, okay, therefore it's constant acceleration, it's going to be constant gradient, as I was saying, then the average velocity for this trajectory is the midpoint of the line segment joining u and v, that is, u plus v over 2, the midpoint, okay. Now, That is what this beastie is. That's what I'm saying. Okay, now we're going to put this new little gremlin here into there. That's what I'm going to do, into Mr. Equation star. Yes, I'm just showing it there for you on the graph. Okay, V average is U plus V over 2. Yes, hence the average velocity from right up here is equal to U plus V over 2, and that's equal to X over T. Now we're getting somewhere. Have a look at this. Hence, X, if you rearrange this thing a bit here, is equal to U plus V over 2 times T. Equation 4. That's it. That's equation 4. That's the other one. That's the fourth formula for constant acceleration, okay? That's it. Now, that one doesn't get used as much, but it's still important to have it up your sleeve if you need it, all right? Now, what I'm going to do now is I'm going to do a marvellous little graphical expose to illustrate this last equation graphically, yes? Now, first of all, I'm going to do a graph where the velocity is constant, no acceleration at all, just to show you something. You know that the displacement is equal to the velocity by the time. You know that, don't you? All right. For example, if you were travelling at 100 kilometres an hour in your car and you did that for 2 hours, you would end up travelling 200 kilometres. That's what we're saying, right? Displacement equals velocity times time, and I just used a very simple example of speed to illustrate the concept, but that works, okay? Displacement is velocity times time. Now, let's do that on a graph. Okay, we've got a constant velocity in this scenario, all right? Constant velocity, up right along there to that particular final time. Oh, yes? Yes. Now, what is that? What have I done there? Well, guys, x equals v times t. Now, if v is here, that height there, and t is this length along here, then v times t represents the length times the width of this rectangle defined by the axes and this green line and this blue dotted line here. So in other words, this height times this width is an area. So x equals v times t can be represented by the area under the velocity time graph. You get that, don't you? I think so. Now, let's have a look at the second scenario I want to show you, and I've got a graph of that as well for you. We know that for constant acceleration this time, this was zero acceleration, just to illustrate the point of the area under the graph kind of thing. Now, if we have x equals u plus v over 2 times t, that's in a constant acceleration scenario, which I'll show you the graph for now. There it is. There's u, and var is v. Now, have a look at this. That area too, that area as well, guys, is the displacement. It is the displacement, because the displacement is in fact the area under a velocity time graph, even if the velocity changes, right? Now I'm going to show you a beautiful little way of illustrating why this formula here works, okay? With that in mind, if I take the average velocity, u plus v over 2, as we found over here, this business over here, the midpoint of the line segment joining u and v, if I take that average velocity, right, and I draw a horizontal line, a constant velocity equivalent, right along this time span here from 0 to t of u plus v over 2, you watch what happens. If I was to cut that little bit of area out there, delineated by that triangle, get the scissors and cut it off, and dump it over there into that hole, then I would actually get, watch this, aha! I've got the same equivalent area as I had before with the sloping line delineating the change in the velocity with time. I've got an equivalent area, but it's actually a rectangular area, and it's an equivalent constant speed of u plus v over 2, and it gets me the same area under the curve, so it gets me the same answer for the displacement as the original graph did, where we had the sloping line of velocity. Okay, so you can see quite clearly, guys, that u plus v over 2 times t, in other words, this times this, gets me the area under the curve. So that's a graphical way of illustrating this formula for a constant acceleration scenario. Okay, so x equals u plus v over 2 times t in this situation here. This is this which is equal to the rectangular area under the u plus v over 2 velocity time graph, equivalent to the area under the original velocity time graph which we had in the first place with the sloping line for velocity with time. Okay, so that might help you realise even more deeply and learn more satisfyingly that this formula makes perfect sense. The average velocity here times the time, yes, is the area under the graph. Alright, now we're going to do some examples now. Example 1. We've got a body moving with uniform acceleration. Do you see that? Do you see that? That is your license to drive, guys, with these formulae which we've been deriving for you. Otherwise, you do not have the license to drive, okay? This body has an initial velocity of 5 meters per second, and after 10 seconds, the velocity is 35 meters per second. We have to find, what do we have to find? Okay, the acceleration, the distance travelled in this time, and the time taken to travel 300 meters. All right, I get this. Now, the first thing that I noticed, this distance here, that's stuck in my craw a little bit. I thought, is this a booby trap or what? Because distance can be different from displacement if the thing has changed direction in the midst of the journey and doubled back. So I've got to work out if this thing's doubled back, because I'd just like to work out displacement, if I can. So is the displacement the same as the distance? If the answer is yes, that's fine. If the answer is no, then we've got to do a lot more surgery on this thing to get the right answer for distance. Now, okay, it's got an initial velocity of 5, so that's plus 5. So we could say 5 meters per second to the right, couldn't we? Okay, after 10 seconds, its velocity is 35 meters per second to the right. So I think we can safely assume, guys, that the acceleration is speeding it up in the original direction which it was moving in, isn't it? So therefore, it's not going to change direction. It's just reinforcing the direction that it was already travelling in at the start of the journey. So therefore, we don't have any problem here with this thing changing direction. If the velocity was minus 35, then that'd be a very big cause for concern about changing direction, because it would have changed direction, wouldn't it? It would have gone from plus 5 going to the right to minus 35 going to the left, you see? So we'd have to have a much closer look at that if we were going to work out distance, because it most assuredly would have changed direction. Alright, enough of all that. That's the first checklist thing I like to look at with these things, because I don't want to be tricked by changing in direction. Alright, acceleration. Alright, now, U is 5. I write these out like a nice little list, a shopping list. V is 35, T is 10, and A is, well, we don't know what A is, and that's what we have to find. So I then think, well, what formula am I going to use where A is the only unknown in that formula? And that's that one. You can check them off. I'll plug and chug for you, and you'll see that A is the only unknown. There it is. Do you see? So I can easily solve that for A. So what have we got? 30 equals 10A, therefore A equals 3 meters per second squared, or meters per second. So that's very good. And you can see that A is positive. A is in the same direction as the original velocity, as I was saying. So it's just speeding it up all the time. Good show. Now what's B? B, the distance. Well, that's the same as the displacement, as I've been going on about ad nauseum just before. So this is the formula now. Is this going to work? The distance is the same as the displacement in this case. Yes, we know this. We know, do we know that? Yes, we do. It's 10 seconds. We know that from the above. Yeah, we know everything except this. This is fine. It's plug and chug, guys. So there we go. 5 times 10 plus 3 over 2 times 10 squared. Good show. And that's 50 plus 300 over 2 is 150, yes, so it's 200 metres. It's travelled 200 metres in that 10-second time interval. Excellent show. Good, now let's do C. Now this is the time taken to travel 300 metres, so that's a bit longer than 10 seconds, isn't it? Because it's going to do another 100 metres. So, alright, this is our formula, which you'll see as I do it. We've got x is 300 here, and we have to solve it for t. We know u and we know a, but we don't know t. T is the only unknown, but unfortunately for us guys, it's going to be a quadratic in t, which is a little bit annoying, but we can do it, no problem. So therefore, yes, multiplying both sides by 2, I get that, and then rearrange it right like that to make 0 on the right hand side. Now I did have a little look at this guys, and it doesn't factorise very easily, so I'm just going to go straight for the CAS, okay? And there she be. Solve, and I use x when I usually use the CAS, but I really mean t, you know what I mean. So this is the thing, solve for this thing equals 0 and comma solving for x, I get this beastly looking thing, which if I then go control enter on the TI handheld CAS device, which is the one we use in my school, you get this. Now that's minus 15.91, that's plus 12.57, so obviously you can't have a negative time guys, at least not on planet Earth you can't. But so this one must be the one. The winner is 12.6 seconds is the time taken to travel 300 metres, okay? Very satisfying. Now let's do another one. This is example 2. This is a stone up in the air one now. We're throwing a stone up in the air. A stone is projected vertically upwards with a velocity of 49 metres per second. A, what is the maximum height reached? And B, what is the time taken to reach the ground again? Alright, now, the only difference with these vertical ones, guys, compared to the left and right ones, which we've been doing up to this point, is that you have to decide which way's positive, because they don't really tell you. So I always go this way. Up is the way I usually do positive direction of motion, but you can do down if you want to, as long as you're then consistent with everything that you do according to the way you've chosen, the direction you've chosen positive to be. Okay, I'll show you what I mean. So, alright, here's my checklist. A, therefore, in my frame of reference, because up is positive, gravity in Melbourne, Victoria, Australia is minus 9.8 metres per second is the acceleration caused by gravity at virtually sea level. Melbourne, Victoria, Australia. So therefore A is minus 9.8 because it's down. Downwards, and positive is up in my frame of reference. Now, U is therefore up, it's plus 49 metres per second. V is 0 because we're reaching the maximum height when the thing is stopped momentarily before it starts coming back down again. The final velocity is 0, and we have to work out the x, the displacement. Alright, so now, which formula would you use? Well, I think this is a case for Mr. V squared equals U squared plus 2AX. Don't you? I think so. So let's plug and chug, and chug-a-lug we go. So therefore 0 equals 49 squared minus 19.6x, okay? Now, you notice how I've been consistent with my frame of reference as to what positive is. As I said, if you want to choose down for positive, that's great, but that would be then positive, that would be negative, but everything will still work out. You see what I mean? It will, as long as you're consistent. Therefore, according to my calculations, x is that, which comes out to be that, 122.5 metres. So someone did a mighty fine throw of that stone vertically. It went 122.5 metres up into the air. That's the answer to A today. Hooray! Let's do B. Here's B. What is the time taken to reach the ground again? Okay, that's all right. Time now. We've got to do time. I think what we can do is we can do this formula here. Now, when it reaches the ground, guys, what is x? That is the $64,000 question. X is 0 at ground level. Because it started off at ground level, it finishes up at ground level, so x is 0 at ground level. So if we plug that value in there with x is 0, u is 49, t is unknown, a is minus 9.8, I think we'll be absolutely laughing in no time at all. So there you go. What do we get? Da-da-da-da. Oh, that's very interesting. Look at that. I can take out a common factor of 4.9 t, couldn't I? Look at this. See? Yeah, because 10 times 4.9 is 49, and you get that. So by the null factor law, you can see what's going to happen, can't you? T is 0 or t equals 10. Now, this was x was 0 when you first threw the stone up in the air at time 0, the starting time, and it looks like x is 0 again when t is 10 seconds. So the answer to this, guys, the answer to this is that it takes 10 seconds to reach the ground again. Yes? There it is. It's absolutely fantastic, isn't it? And I think that might be the end. Yes, the end is your friend. So, go forth and practice much, and you will love the license to drive formulae. But please don't drive without a license. If they don't tell you that the acceleration is uniform, aka constant, then you do not have the license to drive. Okay? And don't break the law. And we'll see you soon. Bye for now.